August 30th, 1960, Dallas, Texas. Under the blazing summer sun, thousands of farmers gathered to witness what John Deere executives called their biggest gamble in decades. European-trained engineers had insisted that only high-sophistication, complex hydraulics, advanced electronics, precision-engineered components could meet the demands of modern agriculture. American farms needed power that European methods had proven necessary for survival. But William Hewitt, Deere's president, had bet the company's future on the opposite approach: simple, heavy, overbuilt tractors that any mechanic could fix with basic tools. No computers, no software, just thick cast iron mechanical pumps and hydraulic systems a farmer could rebuild in his own barn. The crowd watched as Deere unveiled machines built on principles that contradicted everything the experts said was required. 65 years later, those same simple American tractors are still running strong, while today's computerized farm rigs sit broken, waiting for software updates and dealer diagnostics. The most advanced tractors ever built, defeated by machines from 1963. The crisis had been building for years before that August morning in Dallas. By 1958, John Deere's beloved two-cylinder tractors, the simple Johnny Poppers that had puttered across American farms for decades, were falling behind. Farmers were demanding more hydraulic power to lift heavier implements, more horsepower to pull wider equipment, and better operator comfort for longer days in the field. International Harvester was gaining ground with their sophisticated multi-cylinder designs. Ford and Case were pushing advanced hydraulic systems that left Deere's traditional machines looking outdated. Inside Deere's Moline headquarters, the debates grew heated. European consultants brought in to study the company's future painted a clear picture. American farming was evolving toward the complex, precision-engineered approaches that had defined European agriculture for generations. Multi-stage hydraulic pumps with intricate valve bodies, electronic controls that could manage dozens of functions simultaneously, sophisticated transmissions with computer-managed shift points. The message was unanimous: simplicity was dead. William Hewitt listened to these recommendations with the calm attention that had marked his rise through Deere's ranks. A University of California economics graduate who had built his reputation in Deere's West Coast operations, Hewitt understood numbers better than most engineers. He also understood farmers. While consultants talked about sophisticated European methods, Hewitt was thinking about Iowa cornfields at midnight, when a hydraulic pump failed and the nearest dealer was 40 miles away. The decision Hewitt made would either save John Deere or destroy it. Rather than chase European sophistication, he would double down on American pragmatism. The new tractors would be powerful, yes, but they would also be rebuildable by any competent mechanic with basic tools. No computer diagnostics required, no proprietary software. No components that required factory-trained specialists to service. Henry Dreyfuss, the industrial designer who had been shaping Deere's visual identity since 1937, shared Hewitt's philosophy from a different angle. While European tractor makers focused on raw functionality, Dreyfuss obsessed over the human element. How did controls feel in a farmer's hands after 12 hours? Could the operator see clearly around implements? Would the seat reduce fatigue during long planting seasons? His design team spent months measuring farmers' arm reach, studying sight lines, testing seat cushions, and lever placement. The engineering challenge was immense. Deere's team had to create multi-cylinder engines that delivered the power farmers demanded while maintaining the mechanical simplicity they could service themselves. The solution emerged from Waterloo, Iowa, where Deere's manufacturing engineers were developing what they called closed-center hydraulics, a system that kept full pressure ready at all times, but only delivered oil flow when an operator moved a control lever. The numbers were revolutionary for their time. While competitors struggled to deliver 800 to 1,000 pounds per square inch of hydraulic pressure, Deere's new system would generate over 2,000 pounds per square inch with 20 gallons per minute of flow capacity. More importantly, the entire system could be rebuilt with standard wrenches and a basic understanding of hydraulic principles. No electronic diagnostic equipment required. The tractors taking shape in Waterloo reflected this philosophy in every component. Cast iron center sections thick enough to withstand decades of stress. Axle housings built like bridge foundations. Six-cylinder engines with mechanical injection pumps that could be adjusted with simple tools. Transmissions with synchronized gears that operators could repair in their own shops. As August 30th approached, Hewitt knew the stakes. Deere had invested millions in tooling for the new generation line, the 1010-2010, 3010, and 4010 models that would either establish the company's future or bankrupt it. The Dallas unveiling would be make-or-break moment, with thousands of farmers, dealers, and industry observers watching. The event itself exceeded even Hewitt's ambitious expectations. Farmers walked around the new tractors, testing controls, examining hydraulic fittings, lifting hoods to inspect engines. The response was immediate and overwhelmingly positive. These machines felt right, substantial without being complicated, powerful without being fragile. Orders began flowing in before the demonstration was complete. But even as celebration filled the Dallas fairgrounds, sobering questions remained. Could tractors built on 1960 principles survive the technological revolution that was clearly coming? Computer guidance systems were already being discussed in agricultural journals. Emissions regulations seemed inevitable as environmental awareness grew. European manufacturers were promising tractors with electronic fuel injection, automated transmissions, and integrated data systems. The 4020, which would emerge from this new generation foundation in 1963, would ultimately produce 184,879 units over its 9-year production run. Nebraska test results would confirm 95 horsepower at the power takeoff and 84 horsepower at the drawbar, with hydraulic systems delivering 2,250 pounds per square inch at 18 gallons per minute. These numbers represented genuine capability without compromise. Yet as farmers drove their new tractors home from Dallas dealerships, the fundamental tension remained unresolved. Hewitt had won the first battle by choosing American simplicity over European sophistication. The war, however, was just beginning. Technology would continue advancing, regulations would multiply, and eventually someone would have to answer the uncomfortable question: could a tractor philosophy rooted in mechanical simplicity survive in an increasingly electronic world? The answer would take decades to emerge, written not in boardrooms or engineering labs, but in the daily reality of farms where uptime mattered more than sophistication, where a working tractor in the field was worth more than a computerized machine waiting for software updates. The real test of Hewitt's philosophy would unfold not in the spotlight of Dallas, but in the industrial heart of Waterloo, Iowa, where foundry workers and machinists translated ambitious concepts into tons of cast iron and steel. The Waterloo Works had been John Deere's manufacturing backbone since the early 1900s, but the demands of the new generation line pushed the facility into uncharted territory. Inside the foundry, molten iron flowed into sand molds sized like small bathtubs. The center sections that would house each tractor's transmission and hydraulic systems emerged from these molds weighing hundreds of pounds, more than competitors deemed necessary. Where other manufacturers calculated minimum material requirements and added a modest safety factor, Deere's engineers specified wall thicknesses that seemed almost wasteful. The philosophy was deliberate: build components so robust that normal wear and stress would never threaten structural integrity. The 404 cubic inch six-cylinder engine that would power the 4020 represented this overbuilt approach in mechanical form, displacing 6.6 liters. The power plant featured a cast iron block with cylinder walls thick enough to handle multiple rebuilds. The mechanical fuel injection pump mounted directly to the engine block, eliminating the complex high-pressure lines and electronic controls that European manufacturers were beginning to adopt. A competent mechanic could adjust injection timing with basic tools and rebuild the entire fuel system on a shop bench. Nebraska's test engineers would eventually document the engine's capabilities with characteristic precision: 95 horsepower at the power takeoff, 83.8 horsepower at the drawbar, maximum pulling capacity of 11,249 pounds. These numbers represented genuine capability, not marketing fiction, backed by the most rigorous tractor testing program in the world. But the engine was only part of Waterloo's overbuilding strategy. the hydraulic system embodied American engineering pragmatism in its purest form, while European tractors featured complex multi-stage pumps with intricate valve arrangements. The 4020's closed-center system operated on elegantly simple principles. A single pump maintained 2,250 pounds per square inch of pressure in the system at all times, ready for instant response when an operator moved a control valve. The engineering advantage was immediate and practical. Traditional open-center systems circulated hydraulic fluid continuously, generating heat and requiring larger reservoirs to manage thermal stress. Deere's closed-center approach pumped oil only when work needed to be done, keeping the system cooler and delivering 18 gallons per minute of flow with snap response that farmers could feel in their implements. More importantly, for long-term durability, every component in the hydraulic system could be serviced with standard tools. The main pump bolted to the engine block with 6 conventional fasteners. Individual control valves, the selective control valves that would become legendary for their reliability, mounted in the rear casting with simple threaded connections. No special diagnostic equipment required, no proprietary software to navigate. A farmer with mechanical aptitude and a decent tool collection could completely rebuild the hydraulic system in his own shop. The transmission followed the same overbuilt philosophy. Synchro range gearing provided 8 forward speeds and 4 reverse, with synchronized shifting that operators could master quickly. The gear sets ran in thick gear oil within a cast housing designed for decades of service. Even the differential and final drive components reflected Waterloo's abundance approach: larger bearings, thicker gear teeth, and oil capacity far exceeding minimum requirements. Assembly line workers in Waterloo understood they were building machines meant to work for generations, not just seasons. Quality control focused on fundamentals that would matter years after purchase: proper torque specifications on every fastener, hydraulic system cleanliness that would prevent premature wear, engine break-in procedures that ensured optimal performance from the first hours in the field. The parts supply chain reflected this long-term thinking from the beginning. John Deere's Riemann program guaranteed that critical components, hydraulic pumps, clutch assemblies, fuel injection parts, would remain available long after factory production ended. Independent suppliers like A&I Products built parallel inventories of replacement parts, ensuring that even small-town implement dealers could keep 4020s running. The proof of Waterloo's overbuilding philosophy would emerge over decades, documented in farm records and shop logs across the Midwest. Tractors with 10,000 hours on their hour meters continued row cropping and tillage work with nothing more than routine maintenance. Engine rebuilds at 15,000 hours often revealed cylinder bores still within factory specifications. Hydraulic pumps that other manufacturers would have replaced twice still delivered full flow and pressure after 20 years of seasonal use. These durability achievements weren't accidents or lucky breaks. They represented the deliberate engineering choices made in Waterloo's design offices and manufacturing floors. Every casting specification, every material selection, every assembly tolerance reflected the conscious decision to build machines that could be repaired rather than replaced, maintained rather than upgraded. The 4020 that rolled off Waterloo assembly lines between 1963 and 1972 embodied this philosophy in 184,879 identical examples. Each tractor weighed between 8,225 and 9,560 pounds depending on configuration, mass that competitors criticized as excessive but farmers valued as substance they could feel in challenging field conditions. The machine emerging from Waterloo represented more than successful engineering. It demonstrated that American manufacturing could deliver sophistication through simplicity rather than complexity through electronics. But even as the 4020 established its reputation for reliability, the agricultural world was changing in ways that would challenge every assumption about what farmers needed from their equipment. The transformation of American agriculture accelerated through the decades following the 4020's debut, driven by forces that would have seemed like science fiction to the farmers who gathered in Dallas. By the early 2000s, precision agriculture had evolved from experimental concept to operational necessity, while environmental regulations demanded emission reductions that challenged every assumption about diesel engine design. The modern manifestation of this evolution could be witnessed in John Deere's 8R410, a machine that represented the ultimate expression of agricultural engineering sophistication. Where the 4020 generated 95 horsepower from 6.6 liters of displacement, the 8R delivered 410 horsepower from approximately 9 liters, a power density improvement from 14 horsepower per liter to over 45. The engineering achievement was staggering, requiring technologies that would have been incomprehensible to Waterloo's foundry workers in 1963. The engine that enabled this power revolution operated on principles fundamentally different from mechanical injection systems. High-pressure common rail fuel delivery maintained pressures between 1,600 and 2,500 bar, roughly 23,000 to 36,000 pounds per square inch, compared to the few hundred pounds per square inch that characterized older mechanical systems. Multiple fuel injections per combustion cycle allowed precise control of burning characteristics, optimizing power output while minimizing emissions and fuel consumption. Electronic control units managed every aspect of engine operation with computational power that exceeded early space program computers. Fuel maps stored in digital memory adjusted injection timing and quantity thousands of times per minute, responding to throttle position, load conditions, altitude, and ambient temperature. Variable geometry turbochargers modified boost pressure dynamically, while exhaust gas recirculation systems cooled and redirected combustion gases to reduce nitrogen oxide formation. The hydraulic system demonstrated similar advances in capability and complexity. Where the 4020 delivered 18 gallons per minute at 2,250 pounds per square inch, the 8R could provide up to 84 gallons per minute at 2,958 pounds per square inch. 6 individual selective control valves allowed simultaneous operation of multiple implements, each with independent flow and pressure control managed by electronic systems that farmers operated through touchscreen displays. These hydraulic capabilities enabled implements that would have been impossible in the 4020 era. Planters spanning 40 feet or more, with individual row units that adjusted seed depth and spacing based on GPS coordinates and soil conditions determined by onboard sensors. Tillage equipment that modified working depth automatically based on field mapping data collected during previous seasons. Sprayers with boom sections that turned on and off individually to prevent overlap and chemical waste. The precision agriculture revolution reached its full expression in guidance systems that removed human navigation from field operations entirely. GPS receivers accurate to sub-inch precision connected with automated steering systems that could maintain straight lines and curved patterns with consistency no human operator could match. Field mapping software recorded every pass, tracking seed placement, fertilizer application, and harvest yields with geographic precision that enabled variable rate management of inputs. The operational advantages were undeniable. Modern tractors could work longer hours with less operator fatigue, apply inputs with unprecedented accuracy, and complete field operations with efficiency that previous generations of farmers would have considered impossible. Fuel consumption per acre decreased significantly despite higher horsepower, while reduced tillage practices enabled by precision placement systems improved soil health and reduced erosion. Yet these remarkable capabilities came with engineering compromises that would have troubled William Hewitt's pragmatic philosophy. The diesel particulate filters required to meet Tier 4 final emission standards needed periodic regeneration cycles that burned accumulated soot at temperatures exceeding 1,000 degrees Fahrenheit. Selective catalytic reduction systems consumed diesel exhaust fluid at rates that required regular refilling and component replacement. Exhaust gas recirculation coolers, variable geometry turbocharger actuators, and diesel oxidation catalysts added dozens of finite life components to systems that once operated with purely mechanical simplicity. The electronic systems that enabled precision agriculture created similar dependencies on specialized support infrastructure. Starfire GPS receivers, Green Star displays, and various sensor packages required software updates to maintain compatibility with evolving satellite systems and communication protocols. When John Deere discontinued support for older guidance systems like the Green Star 2630 display, otherwise functional tractors faced expensive upgrade requirements or loss of precision agriculture capabilities. Field technicians now arrived at service calls equipped with laptop computers rather than wrenches, running diagnostic software to identify problems within complex electronic networks. Error codes replaced mechanical troubleshooting skills, while component replacement often superseded repair as the standard maintenance approach. The knowledge required to service modern tractors had shifted from mechanical understanding to software navigation and electronic system comprehension. The hydraulic systems that delivered such impressive performance also reflected this complexity evolution. While 40/20 operators could rebuild selective control valves on their kitchen tables, modern electrohydraulic systems integrated sensors, actuators, and control modules that required factory programming and calibration. Pressure transducers, flow sensors, and temperature monitors provided data streams that electronic controllers used to optimize system performance. But these same sensors created multiple failure points that could disable entire tractors. The economic implications extended beyond initial purchase price to ongoing operational costs that farmers were still learning to calculate. Software licensing fees, diagnostic equipment requirements, and specialized technician labor rates added expenses that mechanical tractors had never required. More significantly, the technological obsolescence cycle meant that electronic components could become unsupported years before mechanical wear would have demanded replacement. Despite these complexities, modern tractors delivered productivity levels that justified their sophisticated engineering for many farming operations. The 8R410 could complete fieldwork in weather windows and seasonal timeframes that would have challenged multiple 40/20s working simultaneously. Precision application systems reduced input costs while improving yields, often generating economic returns that offset higher equipment expenses. The fundamental tension, however, remained unresolved. As agricultural technology advanced toward ever greater sophistication, the mechanical simplicity that had defined reliable field equipment for generations was disappearing. The question facing American agriculture was whether the productivity gains from complex systems would prove sustainable when those systems reached the limits of their technological support cycles. The moment of reckoning arrived on a Tuesday morning in October 2023 in a cornfield 40 miles southwest of Des Moines. Dave Hendricks had been combining since dawn, racing against weather forecasts that promised 3 days of rain starting Thursday. His 20-year-old John Deere S760 combine had been running flawlessly through 800 acres of corn, averaging 180 bushels per acre, until the engine suddenly derated to 60% power at 9:37 a.m. The diagnostic display showed an emission system fault code that Hendricks had never encountered. The diesel particulate filter had detected an anomaly during its automatic regeneration cycle, triggering a protection protocol that limited engine output to prevent potential damage. The combine's electronic control system offered no override option, no manual bypass, no way for Hendricks to continue harvesting while addressing the problem later. The machine that had been clearing 40 acres per hour suddenly became an 8-ton obstruction in the middle of his cornfield. Hendricks called his dealer, who scheduled a service technician for the following afternoon, the earliest availability given the peak harvest season. The technician would need to connect specialized diagnostic equipment to identify the specific sensor or component causing the fault, then potentially order replacement parts that might take days to arrive. Meanwhile, Hendricks faced the arithmetic of agricultural economics under time pressure. His custom harvesting rate was $400 per hour when operating, but weather delays cost far more than equipment downtime. Corn moisture content was rising daily as autumn progressed. Grain at 22% moisture on Tuesday would likely reach 24% by Friday, requiring expensive artificial drying that reduced profit margins by 30 to 40 cents per bushel. The local elevator's basis, the difference between Chicago Board of Trade prices and local cash bids, was widening as harvest volumes peaked, further eroding returns on every bushel still standing in the field. By Thursday morning, with rain beginning to fall and his combine still awaiting parts, Hendricks calculated the total cost of the 3-day shutdown, lost harvesting time on his own acres, custom work contracts he couldn't fulfill, damaging relationships built over decades, grain quality penalties from elevated moisture content, storage and drying expenses that would consume weeks of profit. The emission system that protected air quality had inadvertently created economic losses exceeding $20,000 for a fault that involved no actual engine damage. The incident reflected a broader systemic tension that had been building throughout American agriculture as electronic complexity increased. Similar scenarios played out across the Corn Belt every harvest season. Tractors that wouldn't start due to software conflicts between GPS receivers and display systems. Planters that stopped midfield when sensor networks detected anomalies in seed placement algorithms. Sprayers that shut down when weather stations reported wind speeds 1 mile per hour above programmed limits. The frustrations reached beyond individual farmers to industry-wide policy discussions about equipment ownership and repair rights. State legislatures from Nebraska to Pennsylvania had introduced right-to-repair bills addressing farmers' access to diagnostic tools and service information. Agricultural organizations documented cases where electronic lockouts prevented equipment operation during critical seasonal windows, arguing that proprietary software restrictions threatened food production systems. The Federal Trade Commission's 2025 lawsuit against John Deere crystallized these concerns in legal terms, alleging that the company's restrictions on diagnostic tools and repair parts created anti-competitive conditions that harmed farmers and independent service providers. The case highlighted fundamental questions about intellectual property rights versus operational necessity in agricultural equipment markets. John Deere's response emphasized the legitimate complexities of modern agricultural technology. Emissions control systems operating at extreme pressures and temperatures required sophisticated monitoring to prevent catastrophic failures that could destroy engines worth hundreds of thousands of dollars. Precision agriculture software integrated multiple satellite signals, weather data streams, and field mapping algorithms that demanded careful calibration and regular updates to function reliably. The company's position reflected genuine engineering realities. Modern tractors contained dozens of electronic control units communicating through controller area network protocols that managed everything from fuel injection timing to hydraulic valve positioning. Unauthorized modifications to these systems could create cascading failures that endangered operators and damaged expensive implements. Software piracy and counterfeit parts posed security risks that could compromise entire fleet management networks. Yet farmers increasingly questioned whether the benefits of electronic sophistication justified the operational vulnerabilities these systems created. The same GPS guidance that enabled sub-inch planning accuracy could prevent field work entirely when satellite signals were interrupted. Telematic systems that optimized fuel consumption and maintenance scheduling also created dependencies on cellular networks and cloud-based servers that farmers couldn't control or repair locally. The contrast with mechanical equipment became more pronounced as electronic systems aged. A 40-20 with a failing hydraulic pump could often continue operating at reduced capacity, while parts were located and repairs scheduled. Modern tractors experiencing electronic faults typically shut down completely, offering no degraded operation mode that might allow critical work to continue. Independent service providers found themselves caught between farmers' immediate needs and manufacturers' technical requirements. Small-town implement dealers who once rebuilt transmissions and overhauled engines now spent increasing portions of their time navigating software interfaces and ordering electronic components they couldn't test or repair. The mechanical expertise that had sustained rural equipment service for generations became less relevant than computer programming and network troubleshooting skills. The agricultural equipment industry's evolution toward electronic complexity reflected broader technological trends that had transformed manufacturing, transportation, and communication systems worldwide. The capabilities enabled by digital integration, precision application, autonomous operation, predictive maintenance delivered genuine value that justified sophisticated engineering approaches. But the October morning when Dave Hendricks's combine stopped harvesting also demonstrated the fundamental vulnerability of complex systems. Every additional sensor, every software module, every electronic control unit represented another potential failure point that could disable entire machines. The extraordinary capabilities of modern agricultural equipment depended on the continued operation of their most fragile components. The irony was becoming apparent to farmers across the Midwest. The most advanced tractors and combines ever built could be stopped by failures that wouldn't have slowed mechanical equipment from decades past. Technological progress had created unprecedented capability alongside unprecedented fragility, leaving agricultural producers to balance productivity gains against operational risks they were still learning to understand. The solution emerged not from corporate boardrooms or engineering laboratories, but from the practical wisdom of farmers who refused to accept false choices. Across the Midwest, agricultural operations began implementing what became known as the two-tractor doctrine, pairing cutting-edge primary equipment with mechanically simple backup machines that could operate without electronic permissions or dealer interventions. Tom Richardson's operation outside Cedar Falls, Iowa, exemplified this strategic approach. His primary field tractor was a John Deere 8R410 equipped with the full precision agriculture suite, GPS guidance accurate to 1 inch, variable rate application systems, telematics monitoring, and hydraulic flow capacity that could operate the largest implements available. For planting and harvest seasons, when weather windows were narrow and productivity demands extreme, the 8R delivered capabilities that justified its complexity and cost. But Richardson also maintained a 1968 John Deere 4020 that served as his operational insurance policy. When the 8R experienced software conflicts that prevented field work, when diagnostic codes required dealer intervention, when electronic systems created delays during critical seasonal windows, the 4020 could step in without hesitation. No startup sequences, no compatibility checks, no network connections required, just mechanical reliability that responded to operator inputs with immediate, predictable results. The division of labor between these machines reflected their fundamental design philosophies. The 8R handled high-precision tasks, variable rate fertilizer application, GPS-guided planting with population adjustments, herbicide spraying with automatic boom section control. These operations demanded the electronic sophistication that justified the tractor's complexity and cost, generating economic returns that offset the risks of technological dependence. The 4020 handled everything else: tillage work that required pulling power rather than precision, hay operations where uptime mattered more than guidance, accuracy, loader work around the farmyard, running augers and grain elevators, cultivation and field preparation tasks that farmers had been performing successfully for generations. These jobs needed reliable mechanical operation, not computer-managed optimization. The performance comparison between these machines revealed the evolution of agricultural engineering over 6 decades. Richardson's 4020 generated 95 horsepower from its 6.6-liter engine, achieving 14.4 horsepower per liter, respectable efficiency for mechanical fuel injection systems. The 8R410 produced 410 horsepower from approximately 9 liters, reaching 45.6 horsepower per liter, through high-pressure common rail injection and turbocharging systems that would have seemed impossible to Waterloo engineers in 1963. Hydraulic capabilities showed similar advancement. The 4020 delivered 2,250 pounds per square inch at 18 gallons per minute through its closed center system, adequate flow for most implements, with pressure that responded instantly when operators moved control levers. The 8R provided 2,958 pounds per square inch with flow rates up to 84 gallons per minute, enabling simultaneous operation of multiple hydraulic functions that could overwhelm older systems. Yet the mechanical advantages that made the 4020 valuable as backup equipment weren't immediately obvious in specification comparisons. The older tractor's hydraulic pump could be rebuilt on any shop bench with standard tools and replacement seals available from multiple suppliers. The 8R's electrohydraulic system required factory diagnostic equipment for pressure testing and control module programming that only authorized dealers could perform. Parts availability demonstrated the long-term thinking that had shaped Waterloo's original overbuilding philosophy. John Deere Riemann continued supplying factory specification components for 4020 hydraulic systems, fuel injection equipment, clutch assemblies, and transmission parts more than 50 years after production ended. Independent suppliers like A&I Products maintained comprehensive inventories of wear items, filters, and rebuild kits that kept mechanical systems operational without factory support. The aftermarket ecosystem supporting 4020 tractors had evolved into a parallel supply chain that operated independently of manufacturer policies. Machine shops throughout farm country could rebuild hydraulic pumps, overhaul fuel injection systems, and recondition clutches using skills and equipment that hadn't changed fundamentally since the 1960s. This distributed repair capability meant that critical components could often be restored to service within days rather than weeks. The economic logic of the two-tractor approach became clear during seasonal peaks when equipment reliability determined profit margins. Richardson could operate his 8R at maximum capability, knowing that mechanical backup was available if electronic systems failed. The 4020 might lack precision agriculture features, but it could continue field operations under conditions that would disable more sophisticated equipment. Insurance companies recognized this operational strategy by offering premium discounts for farms that maintained backup equipment capable of completing critical seasonal work. Risk assessors understood that mechanical redundancy reduced the probability of weather-related crop losses when primary equipment experienced downtime during narrow planting or harvest windows. The cultural implications extended beyond individual farm operations to rural communities where mechanical knowledge remained valuable alongside computer programming skills. Young farmers learned to navigate software interfaces and interpret diagnostic codes while also mastering hydraulic system troubleshooting and engine rebuild procedures. The combination of electronic sophistication and mechanical competence created operational flexibility that neither approach could achieve alone. The wisdom embedded in this dual approach reflected uniquely American engineering pragmatism, the recognition that optimal solutions often involved using the right tool for each specific job, rather than seeking universal answers to diverse problems. Modern tractors maximize seasonal productivity through electronic optimization and precision control systems. Mechanical tractors maximized operational longevity through rebuildable components and distributed repair knowledge. The two-tractor doctrine represented more than equipment strategy. It embodied the agricultural industry's mature response to technological complexity. Rather than abandoning mechanical reliability for electronic capability or rejecting electronic advantages for mechanical simplicity, successful farming operations integrated both approaches strategically. American ingenuity had succeeded twice, first by overbuilding tractors that any mechanic could maintain indefinitely, then by over-integrating performance through electronic systems that delivered unprecedented capability. The smartest farmers used both philosophies and refused to accept that choosing one meant abandoning the other.